Hello, students. Imagine opening a bottle of vinegar in your kitchen. The sharp sour smell you sense is from acetic acid, a small carboxylic acid. Now, let's explore how these acids appear physically. Aliphatic carboxylic acids up to 9 carbon atoms are usually colorless liquids at room temperature, but they have unpleasant odors. As the carbon chain grows longer, the acids become wax-like solids and are almost odorless. Why is that? It's because their volatility decreases with increasing molar mass. Another key feature is their boiling point. Carboxylic acids boil at higher temperatures than aldehydes, ketones, or even alcohols of comparable molecular masses. This unusual behavior comes from strong hydrogen bonding between their molecules, which we'll now explore.
Carboxylic acids have a very strong tendency to form hydrogen bonds, which are interactions between the hydrogen of one OH group and the oxygen of another carbonyl group. These hydrogen bonds are so strong that even in the vapor phase, the bonds are not completely broken. In fact, most carboxylic acids exist as dimers in vapor or in aprotic solvents. A dimer is when two molecules of a COOH are held together by two hydrogen bonds forming a cyclic structure. This dimerization is the reason why carboxylic acids have such high boiling points compared to other compounds of similar size. If you look at the diagram on your screen, you can clearly see how the two OH groups from different molecules interact through dotted hydrogen bonds, creating a stable cyclic dimer. Now let's think about solubility. Simple aliphatic carboxylic acids containing up to 4 carbon atoms dissolve freely in water. This is because they form strong hydrogen bonds with water molecules. For example, in hydrogen bonding, the hydrogen atom of the acid's OH group connects with the oxygen atom of water, while the carbonyl oxygen of the acid can also interact with the hydrogen of water. As the carbon chain becomes longer, however, the nonpolar hydrophobic part starts dominating, reducing solubility. That's why higher aliphatic carboxylic acids are practically insoluble in water. So, the balance between the polar COOH group and the hydrophobic alkyl chain decides how soluble a carboxylic acid is. Next, let's shift our focus to aromatic acids. Benzoic acid, the simplest aromatic carboxylic acid with the formula C6H5COOH, is almost insoluble in cold water. This is because the large benzene ring is highly hydrophobic and prevents strong hydrogen bonding with water. However, solubility improves slightly in hot water or in polar solvents. Interestingly, carboxylic acids are also soluble in less polar organic solvents such as benzene, ether, alcohol, or chloroform. This mixed solubility behavior highlights how both the polar COOH group and the nonpolar hydrocarbon portion influence physical properties. Let's test our understanding with some examples. Take formic acid, written as HCOOH. It is completely miscible with water because of its very small size and strong hydrogen bonding. Now look at butanoic acid, C3H7COOH. It is still soluble in water but less than formic acid, since its hydrocarbon chain begins to interfere. Finally, consider benzoic acid, C6H5COOH. Because of the bulky aromatic ring, it is nearly insoluble in cold water. The trend is clear. As the hydrophobic part of the molecule increases, the solubility decreases even though the COOH group remains strongly polar. This principle helps us predict and explain the solubility behavior of different carboxylic acids in exams and experiments.
Finally, let's consider aromatic aldehydes. When a benzene ring carries HCHO group, the compound is simply called benzaldehyde with the formula C6H5CHO. For substituted derivatives, The carbonyl group is given position 1 and other groups are named relative to it as ortho, meta, or para positions. For instance, you can have orthonitrobenzaldehyde, metanitrobenzaldehyde, or paranitrobenzaldehyde depending on where the nitro group sits on the ring. Aromatic aldehydes like vanillin, which gives vanilla its characteristic flavor, retain their traditional names even in opaque nomenclature. This shows how historical usage and systematic rules often blend together in organic chemistry.